Welcome to this new video. So we are still in chapter 1 and now we move to section 1.2 on the Kolmogorov-Chapman equations, which is very important in computing probabilities related to Markov chains. Okay, so let us start by recalling two very important formulas that you may have encountered in a first course in probability. The total probability formula. If we have a sequence of disjoint event whose union contains an event A, okay, so we say that A is contained in the disjoint union of E0 up to EL. Then we can write P of A as the sum over K from 0 to L of the conditional probability of A given EK times the probability of EK. Okay, of course, we are assuming that P of EK is positive. Now, this formula is not difficult to prove. We shall prove actually a more general formula, which is called the conditional total probability formula. If A is covered by E0 up to EL, and moreover, B is an event of positive probability, then the conditional probability of A given B is the sum, as before, of the conditional probability of A given EK and B, this is the intersection here, and it's assumed to be positive, times the conditional probability of EK given B. So they look the same, actually, and one can be deduced from the other, actually, because given B, this is a new probability on the same set, okay? So if you have this, actually, here, if you can take if this is true, take B for every B, then take B to be omega, the universe, the sample space. Then this is a particular case of this. And this also is a particular, but let us prove this directly by going back to the definition. So we know that the union of EK contains A, right? So when I do the intersection with B, I get this. So AB is the disjoint. This is the symbol for the disjoint union, because the EK are disjoint. So AB is the disjoint union of the events AB, EK. Okay? And now I go back to the definition of the conditional probability. P of A given B is P of AB divided by P of B. And by the property of the probability, actually here, the probability of the union is the sum of the probabilities, because they are disjoint. Okay, and that's it, actually. So now once again, I go back to the definition of the conditional probability. P of A given BEK is P of A BEK divided by P of BEK. Okay, and now I put everything inside one sum. And now P of BEK over P of B, you notice that this is by definition the probability of EK given B. And that's it. Okay, so very easy to prove. Now I will use this in order to prove the Kalmagorov-Chapman equations. Okay, so keep in mind this. Okay. We would like to compute two probabilities. P of xn equal j given an initial condition, and the unconditional probability of xn equal j. Now let us start with this one. The other will be a consequence. Okay, so this is actually a probability of a path starting from I. Okay, so what is the probability that starting from state I will be in state j after n transitions? Okay. Let us denote this probability by Pij to the n. And note that by definition that when n equal 1, this is just the transition probability, the one-step transition probability that we denoted by Pij. So Pij to the 1 is just Pij. And once again, please notice that this is not a power of Pij, right? This is just a notation for this probability, okay? So, yeah. And now the first result states that Pij to the n is the ij entry of the matrix Pn. Okay? Not trivial. So once again, this is not Pij times itself n times. Okay, by induction, recurrence. This is true for n equal 1 by definition of Pij and the matrix, the transition matrix P. Okay? Suppose now it's that this formula is true for some integer n. I apply the conditional total probability formula. Okay, so I want to prove that this is just Pij to the n plus 1. Okay, so I take the sequence. So Ek here is just this the event xn equal k. Okay, fixing n. So this is the event Ek. And this is the event B. So the conditional total probability formula tells me that I can write this probability as this sum. Okay. Now, if you look at this probability here, the Markov property tells me that the future is independent on the past given the present. So I can eliminate the x0 equal I. So I can simplify this by saying that this is the probability of xn plus 1 equal j given xn equal k. Of course, here we are considering homogeneous Markov chains. So this is actually what? This is the probability, the transition probability from k to j in one step, right? By definition. So this is just pkj. Okay, and this is what? This is pik to the n, right? So I can rewrite my equation as, so this is pij to the n plus 1, as we observe by definition. This term here is pkj, and this term is pik to the n. Okay, and I can also rewrite it in reverse order if I like. This one is good, actually, enough, fair enough. And what do you notice here? That this is, if you go back to the definition of multiplication of two matrices, this is the general term of the matrix P. Okay, the kg entry of P. Okay, so I just shifted them actually. So because it's commutative. So now this is clearer now. So this is the ik entry of P to the n by the assumption, by the induction assumption, and this is the kj entry of the matrix P. So this is sum actually is what? Is the ij entry of the matrix Pn times P. And that's it. So it follows that Pij to the n plus 1 is the ij entry of the matrix Pn times P, which is just Pn plus 1. So by the induction principle, we proved the claim. Okay, let us deduce some consequences of this fact. First remark, what about n equals 0? We started actually with n equal 1. But it's convenient to set as a convention P of 0 equal the identity. And if we, with this interpretation, P of P to the power 0 is the identity, our previous proposition remains true for n equal 1. Why? Because Pij to the 0 is the probability of x0 equal j given that x0 equal I. And this is what actually? If I equal j, this is just 1. Okay? And if I is different from j, this is 0. So this is I can write it as delta ij, which is called the Kroneker's delta symbol. So delta ij is 1 if I equal j and 0 otherwise. So with this interpretation, actually, P to this, so Pij0 is the elements of the identity. Okay, so we have 1 on the diagonal and 0 elsewhere. Okay. Second remark, if we write Pn plus P to the power n plus 1 plus m equal Pn times Pm, and go back to the entries, what is the ij entry of Pn plus m? It's by definition Pij to the n plus m. Okay, and the general term, the ij entry of this product is, as you know from linear algebra, is Pik to the n times Pkj to the m. Okay, and so these equations are known as the Kolmogorov-Chapman equations. So you have two ways of looking at the Kalmagorov-Chapman equations, either as we did in proposition 1.4, or you can look at them in this way. But they are really saying the same thing. Okay, and now we shall see examples of how to compute these things. Okay, now a corollary of this is that for all states I, j, k, and all non-negative integers n, m, r, we can write Pij to the n plus m is at least equal to Pik to the n times Pkj to the n. Why? Because Pij to the n plus 1 is the sum of all these things. And since all the terms are positive, the sum is bigger than each element. Okay, and we shall use this later. So we can always write this inequality. And if we apply this twice, then you will see that Pij to the r plus n plus m is bigger or equal than Pik to the r, Pkk to the n, Pkj to the m. Just apply the first point twice. Okay, so apply it for r plus n plus m. So you'll get Pik to the r plus n, and then you apply it twice. So if you apply one twice, you'll get this inequality. Okay, so now we have a mean to compute the n transition probability, but how to compute the unconditional probability? That's the system is in state j at time n. This is not difficult. So denote this probability. This is a vector actually. When j varies in S from, for example, from 0 to L, we have a sequence of probabilities that depends on j. So I call this vector of probabilities alpha n. So the components of alpha n are alpha n0, alpha n1, etc. But to compute the unconditional probability, we have to know the initial distribution of the process, of the Markov chain. Okay? Because the Kalmagorov-Chapman probabilities do not depend on the initial condition. Okay? Because they were conditional transition probabilities. Okay, so if we rewrite our equation, this is what actually, this is the total probability formula, right? Just I put instead of ki, this is just the conditional probability formula, right? Because the events x0 equal I when I varies cover is a partition of them, because x0 should be somewhere, right? So the union of x0 equal I is the space omega here. So this is just the usual total condition probability form. So if I rewrite it in this way, this is just alpha n of j. This is, by our definition, Pij to the n transition probability. And this is the initial probability alpha 0 of I, right? I just switched them. And now, once again, what's this actually? If you go back to the definition of the multiplication of a row vector times a matrix, you will convince yourself that this is the jth entry. It doesn't depend on I because we are summing over I. This is the jth entry of the multiplication of the row vector alpha 0 times the square matrix P to the n. Okay? Note the order is very important because I set alpha n and alpha 0 to be row vectors, vector linear. Okay? So the order is important and the operation is not commutative. Okay? So this is row times square matrix will give me what? Will give me a row matrix, as you can check. And that's it. So I can write that the vector of probabilities at time n, this is a row matrix, equal the initial distribution, which is a probability vector, times the probability transition matrix to the power n. Okay, this is very, very simple formula. And note the order once again. Okay, row equal row times square matrix. Lean matrix carry. Now let us see an example. I suggest that you pause the video after and try to do this exercise on your own. Okay, so we go back to the simple phone system. So we had just two states, busy available 0 1, right, or busy free 0 1 0 1. And now the first question is, what is the probability that the phone is busy at time n equal 2 given that it was free at time n equals 0? First question. Second question, what is the probability that the phone is busy at time 3 given that it was busy at time 0? So these are two conditional probabilities. And third question, suppose that initially the phone is busy with probability 0.8 and available or free with probability 0.2. Okay, just an error. But this is redundant because if we know the probability of busy, we know the probability of available because they sum to 1. So as before, alpha n and alpha 0 are probability vectors because the sum is 1. And the terms are, everything is positive or non-negative. So compute the unconditional probability that the phone is busy at time n equal 3. Okay. And this question, use Python to compute p to the n for n equal 4, 5, 6, 7, 8, 9, and see what we observe. So please try at least to pause the video and answer these questions. And I really recommend that you use Python to answer this question because you will see something very important. Okay. So pause the video and try to answer these questions on your own, given what we said about the Kolmogorov-Chapman and their corollaries. Okay. If you have done this, let us continue. I'll give you the solution now. Okay. If we want to compute the conditional transition probability, we have to compute P2. Okay, so it's easy to compute P2, and you'll get this result. Just check with your computer or calculator. Therefore, the transition probability of going in 2 steps from busy to free, I look at P10. So this is 0, 1, 0, 1. What is P10? Is this entry. So it's 0.49. So it's very, very easy now to answer probability questions related to Markov chains. This is the first question. And now later I will give you another way to do that. The second question, we want to compute what? The transition probability in 3 steps, actually, from what? From busy to busy. Okay? So when I do the multiplication, this is equal here. So I multiply P2 by P, I get P3. And I want the probability of staying busy in 3 steps. So going from busy to busy in 3 steps. So I look at P0, 3, and this is, according to what we said, this entry. So it's 0, 5, 2, 6. Now, here, because you are working with small matrices, it's not really a big deal to do them by hand, just for n equal 2, 3, 4. Okay. But for large n and large matrices, this would be cumbersome, and you will need to use computers. Now, note that we didn't, in the question A and question B, we didn't need all the entries. We just needed one entry. So if you don't have a computer and you want to answer this by hand, you don't need to do that. You just need to use the Kalmagorov, apply the Kolmogorov-Chapman equation directly, okay? Because now to compute P3, how many multiplications and additions we needed? The operation of multiplication two matrices actually requires 12 operations, right? So to compute P3, we need 24 operations. By the way, this is important. And this is another method. We can compute P003 with only 9 operations. So it will save you a lot of time. We write the Kalmagorov-Chapman equations first. So there are just two states. So the sum contains just two terms. Okay, this is the first way. So the I here equal 1, the I 0, and here equal 1. Okay, so, or K if you like. So this is the Kalmagorov-Chapman equation for n equal 2, m equal 1, or 1, 2. And now I repeat this. The P002 can be computed by using the Kalmagorov-Chapman equation again. Okay, so this is a double application of the Kalmagorov-Chapman equation. And now, how many operations do I have here? I have 9 operations. So, and if you do that, please check, you'll get the same result. Okay, it's very important because instead of 24 operations, you just needed 9 operations in this case. So when it's big, actually the difference gets bigger and bigger. So, and of course, we can apply it the other way around. We can write P002, so by symmetry. Okay, so they are not the same number. So once again, I can apply in this order. Okay, so here n equal 2, m equal 1. I had before n equal 1, m equal 2. So if I do the same, so the numbers are different actually, not the same thing, but they give you the same result, as you may check. Now, you may ask me what to do. Well, it depends on the question. If you just need one answer, you don't need to compute the whole matrix, especially when it's large. If I give you a 5 by 5 matrix and tell you to compute P3, this will be, if you don't have a computer, this will be really a problem. But this recursive application of Kalmagorov-Chapman equation, okay, requires much less operations. Okay, so you have at least 2 ways of computing. Okay, of course, in this example, we have small things, so it's not a big deal. But it's important to know both approaches, actually. Okay. And so, third question. We want to compute the unconditional probability of being, so this is, we want to compute the probability of being busy after 3 steps, right? This was the question. So I apply the formula alpha 3 equal alpha 0 times p to the power 3. So once again, this is a row times matrix. We already computed P3. And we get a row vector, okay? So here in linear algebra, it's important to distinguish between rows and columns, okay? If we want the probability of being busy at time n equal 3, then we just look at the first component, so state 0 is here. If you want the probability of being free, then you look at the second component. And once again here, actually, you can just compute, if you don't need to compute this power, actually, you just need to, so. Okay, but this is just to illustrate the formula alpha n equal alpha 0 times p to the n. Now, already we observe that P3 is very close. The rows of P3 are very close together, actually. And if you compute P4, P5, etc., you will convince yourself that you are really converging to a stochastic matrix with identical rows. And this is an important observation because it's not a coincidence. It's a particular case of an important theorem that you shall learn. It's called the Ergodic Theorem. It's about the convergence of the matrix P to the n. The matrix P to the n is not always convergent, but in some cases it is convergent, and the limit matrix has identical rows. Okay, so this concludes section 1.2 and concludes this video. Now, in the next video, I will start the classification of states. And since we are running out of time, I'll be posting more than one video per week. Okay, so please, you will have to do an extra effort if you want to finish the program on time. Okay, so thank you for your attention.